So now the whole important topic that we are going to see, it is what is called as a Bezier curve, and we will see the extension of it, and which is called as a B-spline curve, and then the surfaces variety also we will see today. Okay. Now you have to be watching very carefully. I'm hoping that all of you are watching carefully. So the input is actually the set of control points. So these 4 points that you have, B0, B1, B2, B3, are called control points. And then if you join them, but not close them, okay, if you join them, but don't go to the B3 to B0 closure, okay, it's an open polygon. So then this is called as a control points, and then the control polygon, okay, sometimes control net is also being used, okay, the word control net or control polygon. In 3D, we'll see it's used as a control net and then control polyhedron, okay, those are the terms that we will use. In 2D, we will use the term control polygon. So this is the input for it. Okay, note down that this is the input that you give 4 points. In your usual one, if you give 4 points, what you do in your cubic equation, you will try to generate a curve which passes through all the points. Okay, that is not the case here. And we are going to use some kind of a mapping function. Okay, and then generates a curve like you see in the red curve. Okay. So how, okay, I'll give you some more pictures on how this is more intuitive. At this point of time, it may not look more intuitive, but I'll tell you some properties, then you can generate without knowing the mathematics of it. Okay, that is what I'm going to try in today's lecture on it. Okay, now you can see this is how, by using some mapping function between these control points, B0, B1, B2, B3, or control polygon, you can generate a curve which is shown in red. Okay, it follows certain properties. So I'm reasonably sure you can generate the curve without actually knowing the mathematics of it. But let me try that today. Okay, I'm going to try that idea today. Okay, now I'm going to show you more pictures of this idea. So guys, are you there with me? So can some of you speak?
Yes,
Say
sir.
yes,
Yes, sir.
Yes, sir.
okay.
Yes, sir.
Good. Okay, let me go to show more pictures of this idea. Okay, so you can see that. Okay, as I draw a polygon like this, I draw a curve. Okay, and then when I draw a polygon like this, now I can see that the curve is like this. Now I'm drawing a curve without understanding anything. Okay, now you can see there is a curve like this, and then you can see if there is a polygon like this, then I will draw a curve something like this. Okay, now you can see that this is a shape like this and comes back. Okay, so there is something that happens. Okay, can you guys observe anything, that behavior? Can you tell something in relation to how this polygon is and how this curve behavior is? Can you tell, can you find any crucial points here?
Concave maybe, because
Okay, so one thing, that suppose if I have a polygon like, okay, I have drawn it on the right side and I didn't draw a curve like this. So what is the difference between this one and this one?
Sir, is it a 3D shape intersecting with a plane?
This is only 2D. Okay, by the way, we are only talking about 2D. The same thing can be done in 3D also. But this is what I told some time back. So, okay. When just recall what we did in terms of math. Okay, we saw some equations, right? What did we see in those equations? And we discussed, and one of the guy asked some n, there is a problem in n. What is that shape?
sir, are we tangentially meeting at the endpoints and then
Correct.
trying to
That is one
have a
observation.
parallel tangent over
Exactly.
there?
Great. So this you can see that the points B0 and B3, and then the tangents are defined by actually the first and the last control polygon segments. And the first point here, the curve follows tangent and ends with the following the tangent of the last one. So even here, okay, when you are doing here, I'm going to do this. Like you can see the pink one. This again follows the tangent, and this also follows the tangent. Okay. Yeah. So that is a one good point. Any other observation? I mean, you did not answer this question, like at the top.
Sir, at the
Sir,
end
in
point,
that case, tangent is not possible. As we cannot jump across the curve.
So
We can
what is that? I mean, that's what I told some time back, right? This is a very important concept that we are going to use in this class or in this lecture. What is that?
Sir, is it convex?
convex hull.
Suppose you have these 4 points. What is the convex hull of these 4 points?
the quadrilateral.
Trapezium.
Yeah,
That,
the quadrilateral itself. Okay. So the curve has to lie within the convex hull. of this control polygon. Okay, so for example, okay, let me go and come back, otherwise I can't draw again. Okay, so let me again go back to this slide. Okay, now you will see a uninterrupted slide. Okay, now you can see that if I give these 4 points, the one on the left, okay, you can see the convex cell is the polygon plus this guy, correct? Yes or no?
Yes, sir.
Okay, you can see that the curve lies within the convex polygon. So when I draw something like this, okay, which is outside the thing, then that means that is not a correct curve. Yes or no?
Yes, sir.
Correct. So it is not a correct curve. So I have to be maintaining within. So in the same case, in the next guy, you can see that this is the convex cell, okay, bounded by these two lines, and the curve lies within the convex cell and follows the tangent of the first and last. Okay. Now, can you tell any other property? So you can see that even in this case, I can't draw something like this. Even something like this. Why?
It will
What
lie
is this?
outside the convex also.
It is also outside the convex cell because the convex cell is like this. And follow the tangent of the first and the last guy. Okay, so anything else? Any other observation that you can make? So we talked about curve lying within the convex cell, and it has to follow the tangents of the first one and the last one. Like for example, okay, if I have a polygon like this, okay, so can I draw a curve like this? Something like this, is it possible?
No, sir.
So,
Because
so that means what? But I can draw a curve, something very, very much like this. So what is the difference between the two things that I drew?
so the second one lies inside the convex cell.
Okay, and then first one didn't lie. Okay, this property we already saw. Okay, so anything else that you can think of? Okay, let me try a polygon like this here. Okay, like this is a polygon. Okay, so now I am going to draw a curve. Let's say like this. So what is that? I kind of followed. Which is the one that I kind of followed?
They're very similar to the original shape, but just
So, okay, that is what does that mean? Is that when I have an input as a control polygon, the curve kind of follows the control polygon. Okay, and also maintains properties like it is the tangent to the first and last guy. It never goes out of the convex cell. And the most important property is that it doesn't oscillate something like this. Okay, it always closely follows your input, which is the polygon itself. So when I have a polygon like this, I can draw a curve like this. Okay, sorry, not a very great curve, but something like this. So it doesn't oscillate too much. Okay, I mean it's that is the whole beauty of this Bezier curve. Like you can, as I give you a control polygon, you can try to draw the curve. Okay, without knowing, we have not understood anything in terms of how this mapping function between the input and the curve is. Okay, but all I am doing is now what I am giving an intuitive feeling of how the curve is going to be. Okay, guys, did you get this? Understand this idea?
Yes, sir.
And remember, this is the convex cell. Okay, so the whole idea is that these are the properties. Okay, the curve always lies within the convex cell, which we saw, and curve does not oscillate. Like for example, when I have a polygon like this, it doesn't go like this. Okay, so that is one thing that you have to observe. So it will always be at a lower oscillation mode. It never oscillates more than the polygon itself. So for example, if I have a polygon like this, I won't have a curve like this. There won't be any undue oscillations on that. And also it closely follows the control polygon. I mean, this is a very, very important point, very intuitive one for you to design that. The convex cell is the one. And then curve does not oscillate, as we have seen that, and we'll see why it doesn't oscillate. And then the curve, remember, if you have a control polygon like this, let's say this is a control polygon, V0, and you can do whatever, V1 up to. And you can see that the curve passes, it's kind of a disadvantage. Also, the curve passes only the first and last point. Okay. So it doesn't pass through any of the, like, it is not a curve, like, it is not like this, something like this. So except it is not an interpolation, okay? That is why it is not an interpolation, okay? So it is not an circle. Yeah.
Sir, a quick question regarding this. Sir, is it possible, say, like, if we have the points arranged in a way that it is forced to pass through some of the other
Okay,
points?
that's a very interesting question. I will come back to that question. Okay. So we'll see in some special cases also, we'll see it won't pass through. Okay, I'll come back to that point after we discuss one more intuitive algorithm for this same curve. Okay, so I'll come back to this. Okay, is that okay? Fine.
Yes, sir. Yes. Thank you.
Okay. So we can see that the curve passes only through the first and last control points. Okay, and the curve, as we saw, it closely follows the control polygon. Okay, and we can see that as I showed you some example, if I have something like this, I can easily draw the curve. I mean, I don't need to know any of this equation. Okay, that's the beauty of this. Maybe, of course, I'm a little bit more experienced, but still, I'm telling that you can intuitively draw. And the only problem here is that, as we see more on this, the degree of this curve will be equal to the number of control points. So we have B0, B1, 2, 3. So the degree of the curve will be 6. That is the only kind of drawback, you would say. But still, even at 6 or even at 10, it won't have oscillations as you saw in other kinds of interpolation method. Okay, that is guaranteed. There won't be any undue oscillations for you. And that is the beauty of it. You can have a polygon like this. Okay, and you won't get a curve with like this. Okay, you won't get. And that is one of the beauty of this Bezier curve. And you can see the extension to surfaces also work in a similar manner. And we saw this property of tangents coinciding with the starting and end pair of control points. Okay, like this, it always starts with the tangent at the first guy and ends with the tangent to the last control polygon segment on. Okay, now guys, all of you hopefully have a pen and paper with you. So can you draw the Bezier curve for these control polygons? Each one are different polygons. So okay, take a minute, or maybe it won't take that much. So all of you are ready with your pen and paper? I need to go to the, where is this? So all of you have your pen and paper now? Okay, can you just draw this Bezier curve? So put it chat box. Once you finish, you put done. Okay. Oh, so fast. Okay. Fantastic. So I think, yeah, very good. So this is like a lab session, okay? Because coding this will take a lot of time. I mean, at least reasonably more time. Okay, so anybody not able to do this? That means probably he or she is not listening. So I need more responses, please. So I'll give you another maybe 1 minute. So many of them I already drew, but okay, what is the degree of the curve for the first polygon? Which has how many points? Control
Yes,
points. How many
there's
control
3
points?
control points, sir.
So at the degree should be 2,
Number of
right?
control points?
It's 3, sir.
Okay, it is 3. Okay, I should have mentioned it clearly on that. Okay, so okay, we'll count it from 0, 1, 2. That last index is n. Okay, I kind of little bit messed up on that. So the last index is the degree. That means if you have 3 control points, what will be the degree?
2, sir.
Okay, 2. So I kind of little bit messed up there. So if you have 3 control points, it will be of degree 2 curves. So if similarly, if you have 5 control points, what will be the degree of the curve?
4.
Okay, it will be a degree 4 curve on it. Okay. So all of you, okay, I'll also try to draw this shape of this Bezier curve on these things and look at your answers and see if it is matching with my answer. So you will have something, it has to follow the tangent at the first and last and something like this. Okay. Very bad drawing. Okay, let me go back. Okay, so let me try to redraw. See, remember it has to follow that. Okay, something like this. Is that what your answers are telling? Did you get a similar answer to what I drew? Okay. Remember, I did not even draw something like this. Okay. Not even like this. But this can also be built, but not in a Bezier form. But in the other form, we can do these points. So you can see the other answers. I think if I do roughly, you can see that something like this. And then, this guy would be closely follows your control polygon in essence. Right? So the other one would be something like this. This is not exactly right because it doesn't look like a degree pi curve. Something like this. Okay. So did you guys?
Sir, how will the roots be determined for these curves, sir? Except
we
those
haven't
two
seen
ends.
the equation yet, right? We are not. What do you mean roots? This
Like
is
in the
not.
sense, the only via roots we
This is
determine the
not a root. We are
polynomial,
only
right?
finding the curve.
Yeah, sorry, that's what I meant. Sorry.
Okay, this is not a root finding, solving a minimization or a maximization, at least not yet. Okay. So if you are confused with the optimization technique, this is not yet an optimization problem yet. Okay. So this is only a direct mapping from the input, which is the set of control points. Also, we call that as a control polygon to the curve. Okay. We are only finding how the curve is from the input set. Okay. We are not solving anything more than that. Of course, we can find maxima, minima, where happens and so on. We'll come back to that, but we are not exactly a root finding at this point of time. Okay, are the other guys any other doubts?
Sir, how are we deciding on the hump that we are getting?
So
Like how
it
much
won't be
hump?
below B2. Okay, I think it won't be below B2. I think it closely follows the control polygon because it is okay. One of them asked it something like this, right? Will it be something like this? So when you have this non-concavity happening, it also tries to follow the non-concavity. I think who asked Abhishek Das, right? Abhishek. Yeah. So it is like, that is why it closely follows the control polygon structure. So when you have a non-concavity, like you can see that this point is of non-convex, right? Sorry. Non-convexity or a concavity. The curve also will exhibit a similar behavior, like what kind of happens in a sense here. Okay. So this is not actually a non-convex, but this kind of flips on the other side because of the degree, because the 4 control points and you have a third degree. And then you can see that there is a non-convexity coming in because of this, and your polygon also kind of captures that kind of non-convexity. So that way it closely follows the input control polygon. Is that solve your kind of give a better feel for that answer? Okay, right, good. So any other questions? So you can now see that, we have not seen a cubic equation, or we have not seen some, a lot of equations to write all to find out how the curve is going to be in a reasonable manner. Okay, we may not have exactly reproduced this, but we have done something on that direction. Okay, that is the whole idea of this, what is called as ab initio design, where you get an intuitive feel of generating the curves or surfaces. That is very important. It may not be exactly, as you asked, exactly pass through this, pass through that. It may not, because this is like a free form design. Okay. So the whole idea is that not to force everything to pass through. So yes, in some conditions, yes, you may have to do that. We'll also see how it is possible to do that. Okay. Moving ahead, and can I move ahead, guys? Are you all there? So all of you put an yes, please. I'm having only 15 guys or guys. Okay, I want to see all of you putting an yes. How many of you? Maybe 30. So put an yes, and let me get a better feel of attending the lecture. Okay. So any questions you ask, okay, don't worry. I mean, as I've been saying, if I know the answer, I will tell the answer. Okay, if I don't know, I will go back and look at it. No problem on that. Nobody knows everything in this world. Okay, so don't worry about all that. Ask a question so that it gets clear. Okay, now what we have not seen is how this curve is being computed. Okay, you can see the beauty of it. We have not we have not seen any equation. We have not computed how given this B0, B1, B2, and so on, how is going to map. Without that, we are able to draw that. Okay, now maybe we'll go back to some basics on how to actually capture that in terms of equation. Okay, so there are two ways in which, as far as I know, two ways in which you can do the Bernstein basis. This is called using the basis function approach. And there is one more that's called as a de Castillo algorithm. Okay, de Castillo algorithm is, I would say, much more intuitive on that. Whereas Bernstein, it's also okay, but it gives more mathematics to the behavior of the curves. Whereas de Castillo algorithm gives more feel for how you get the curves. So these two are in slightly different angle, but you can see both are giving some kind of an idea about the curve. Okay. So now, now you can see bamboozling little bit of these equations. Okay, now all of you, I guess, drew this curve without any problem. But now you have to look at the equation. Okay, this is looking very too much at this point of time, but I will try to dissect this equation better. Okay, so this is the entire form, and you can see these BIs are the input. You can see B0, B1, B2, B3, and so on. And this is what is J is called as the basis function or the Bernstein basis. Okay, popularly called as a Bernstein basis. And this equation goes like this. Okay, what is this notation?
NCI.
Okay, NCI, which is basically your binomial expansion. Okay, and then you can see the t power I, 1 minus t power n minus I. Okay, this equation looks a little bit scary. Okay, now it's actually not a very scary equation. We'll try to give some examples, and then we can actually directly write this equation without, yeah.
So is that function? It looks similar to the binomial
It is
distribution.
a binomial only. It is a binomial expansion. So NCI is a binomial expansion only. That n
No,
dot
sir, I meant like when it comes to probability, we have binomial distributions.
Correct. So of course you don't have to go to the distribution level. It is only at the expansion level in this equation. But I'll also give you a better feel that you don't have to remember all this. You can directly write the equation for any degree. Okay, I'll give you a certain feel for that also. Okay, now let us little bit understand this equation in detail. Okay, now you can see that this J and I basically okay, basically it amounts to, my internet is lost. Okay, I'm coming back. Okay, so basically you can see that if you have n equals 2, okay, you will have J20, J21 and J22. Okay, isn't it? So what is J20? J20 is 2C0. Okay, 2C0 is what?
It's one, sir.
2C0 is 1. What about 2C2?
1.
It will also be one.
It will also be 1. Okay, what about 2C1?
2.
It is 2. So you can see that this 1 to 1 comes here. Okay. Now you can see that because this is t power and this is n minus I. So basically you switch between I and n minus I. So that means what? When you have 2 here. Okay. So remember that this is I and n minus. So for I is 0 initially, then this is 2 minus 0. So you can see that this 1 minus t square will go for a first n, whatever this n here. And then it switches between t power n. So you'll have 1 power here, 1 power here, and again the other one will go to 0 and 2. So you can see that this will follow 1 minus t square, 1 into 1 minus t square. And then you can see this is 2 into t into 1 minus t second guy, and this guy will go to 1 into t square. Basically the powers added together will become 2 or n. Okay. So if you elaborate this for, this, maybe you get some feel. I'll go to the next equation for n equal to 3. So you should be seeing that.
Sir, just a minute. Can we just go back to the previous one? A quick question regarding
This one?
Yes, sir. So
Okay.
here, we have B0, B1, B2 there, which is drawn there. How do we account for what angle is made between B0 at B1 basically? Is there some way to
No need. You
understand
can
that?
have any angle. See, if you are in 3D space, you can have any element or the coefficients or this. So it doesn't matter. See, B0, B1 are coordinates of a point. That's all. It has X0, Y0, and Z0, let's say. And this is X1, Y1, Z1, and so on. You can have it anywhere. Doesn't matter.
Okay, sir.
Okay. So
So
these are just
even a
coordinates of the points.
Okay. So even if B1 was collinear with this almost, then also this will be collinear finally.
Yeah, no problem on that. But we'll see. Yeah, true. No problem. It can be anywhere. It can be collinear also. The curve behavior will be okay. That's a good point. But so, like, if you have three guys B0, B1, and B2, collinear, let's say, where will the curve lie? What
So
is
the
Should be
convex?
on the line itself.
convex hull will not
What is the
have any
convex?
area, sir.
These 3 points.
It won't have
Yeah.
any area, sir. So the curve will have to be the same.
But what will be the convex cell in terms of actual B0, B1? What will be the thing?
Straight line.
So it is same
Just
as
a-
your control polygon itself. Yeah, as you said, it won't have any area. So where will the curve lie?
On the line
It will also
itself.
be
Okay.
the straight line,
In
sir.
this particular case, the curve has to lie within the convex cell, and the convex cell itself is a collinear one, which is a degenerate case. Okay. So, like for example, if you have a control polygon like this, okay, your curve will be like this. Correct? Yes,
Yes.
or no? Okay, now remember I'm flattening this guy. That means I'm bringing this guy down. That means what? My curve also will come down. Correct? So if I have 3 points like that, now my curve also has to follow that. So the curve also will be like this.
Okay.
I mean, this is only a very special case on it. Okay?
Yes.
Because it cannot go outside the convex cell, right?
Yes.
And the convex cell
Sir,
itself is an area.
Another question is, should it be equidistant? As in B0,
No,
B1 need not be.
That nothing to do with equidistance. You can have any distance, no problem.
Okay, sir. Thank you.
Okay.
These two
Yeah, and it can have any dimensions. Okay, we are only looking at more 2D because that is what we can draw. Anything other than that, we may not be able to draw, but we are only able to draw this, so we are showing it on 2D. In principle, in practice, you can go for any dimensions. It's only vectors, right? As I said, B0, B1, B2 are all vectors representing each of the point. Then it is all matrix multiplication computation. It can hold good for any dimension. Of course, we'll have a problem in visualizing at any dimension, but that is only a problem at other front, but not in terms of mathematics. Okay.
Yes.
Now, okay, let me just go to the n equal to 3 case. So you can see that n equal to 3 case, we will have J30, J31, J32, and J33. What is J30? So remember, this will be 1 into 1 minus t whole power 3. Remember, there are two terms, 1 minus t and t. Okay, this will alternate between 0, 1, 2, and 3, and the summation becoming 3 after that. So if this is 2, and this has to be 2. Okay, sorry, and depending on the power here, what is that 3 and all? Okay, so if this is 3, sorry, this has to be 0. Because total power has to become the number of control points, or the n, which is 3 here. Okay, so if you have 1 minus t square, then that term has to be t and so on. So you can see that J30 will be 1 and J33 will also be 1. And then this coefficient, if you compute, it will be 3, and this coefficient also will be 3. Okay. So these coefficients, if you can think of, it will follow this picture. What is this picture?
It's a Pascal's triangle.
It's a Pascal triangle. So, and then if I have 1 here, and then you can see it is 1 minus t square here, and this will be 1 minus t into t, and this will be t square. In a similar way, this is 1 minus t cube. What will be this term here? If you plug in the equation, it will be
t into 1 minus t square.
okay, t into 1 minus t square. What about the other one? That
T
will be
square into t
t
square
square
into 1
into 1
minus
minus t, and this will become t cube.
t.
Correct. Okay, now all of you take a paper and pen and write the equation for this guy. That means n equal to 4. The number of control points is 5. So how can you write this equation quickly? You have to plug in this B0, B1 suitably. So what will be the equation after this? Why silent? You can directly read right from there.
So like 1 into 1 minus t power 4 plus 4t into 1 minus t cube.
Remember B0, B1 also. You have to put this B0, B1 also. Remember B0 is the input, right? You have to have account for input also. So it will be B0 into 1 minus t power 4 plus
B1, 4b1 into t into 1 minus t cube plus 6
correct.
b2 t square into 1 minus t square plus 4
Correct.
b3 dot 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 like that.
Okay. So all of you got that idea?
Yes, sir.
Sir, I had a doubt.
Okay. So if you want to have this, you can directly write this. Okay, just a minute. P of t equals, you know that you have to take the input. Okay, B naught. Remember, this is only one. That means 1 minus t into power 4 plus B1. And then you need that this is the 4 coefficient. And then you can see this go down by 1 minus t cube plus and then t. Then you have to B2. Then you see that 6 comes in. Okay, then this 1 minus t square and then this becomes t square. And then plus b3 dot, I mean there's a 4 there. So this is 1 minus, instead of go square, it will be 1 now, and this goes to t cube. And then you can see there is a coefficient 1, b4 dot 1, and then you can see this is t power 4. Okay, now you can keep expanding this classical and write for any degree n. Okay, now is it okay, guys, all of you? This is if you write in terms of equations, but you can see that if I give a polygon like this, well, and you can see that this is the equation for this polygon, because for each t, remember t goes from, it's a parameter on the curve, t goes from 0 to 1, and then you can know that without calculating this equation, you can see the curve is going to be like this. So this is the intuitive nature of this entire Bezier curve, and you don't have to know the equation for that matter. Okay, but you always better to know the equation. Okay, now somebody wants to ask a question. Can you ask?
Yes, sir. Is this not like a weighted average across time in which the points are what we're waiting
Correct,
after?
correct. This is same as what is your equation. This is same as your
As the convex thing, जो हमने पहले
as the
did earlier.
convex thing, right? So remember, t is between. That's an excellent point. That's what actually I'm coming to in the next slide, I guess. Let me try that. Okay, this is exactly the point that I'm coming. Now you can see that for degree 2, this is the same equation as what you have, what you saw before, that in terms of p, but we are seeing in terms of alpha naught and b naught. Okay, the same as your convex combination. Okay, now what this leads to? What is the implication of this? What is the implication of this entire thing? In terms of curve, where is it lying?
So inside the
Inside the
convex
convex cell, sir.
Is it inside the convex cell of the control polygon, right? So when you have a control polygon, it's this is the convex cell, and your curve will always lie within the convex cell. Okay, that is why this relation is very important, and I think it is very good point that I think one of you mentioned this, and as coming back, and this is holds true for any any degree curve on that. Okay, same thing.
Sir, could you please explain why it will lie inside, or like why won't it track that?
Okay, okay. So that is a good point. Okay, so first you understood that it will lie within the convex cell. Okay, now if you substitute t equal to 0, what it will happen? Let's say you take any of these equations, second degree or a third degree, doesn't matter. Okay, now if you substitute t equals 0, what it will happen?
So we'll get the first point. B naught.
You get the first control point B naught. Okay, remember that has to lie on that control point. That is what we said. And for t equal to what is here? Let's say if we have t equals 1,
Then it's at the end point. It has to start at the first point and end at the end point.
it will end at B2 in the case of second degree, or it will end in B3. Correct? Yes or no, please? Okay.
Yes,
Now take any other t, and what will happen to this equation?
Okay, just because we have only a single parameter, this is happening in this way. As
So
in
now
we
if you
start
take
and
any
end.
equation, others are not going to zero, right? Okay. So
Yeah,
that only
okay.
one of the alpha is going to play a role. Okay. So you can see in the other case, all term became zero. And then this alpha not played a term in bringing it to B naught. And similarly, you can see that all other terms became zero for t equals 1. And you can see only alpha 3 play a role. In all other points, you can see other alphas are not going to become zero. But even though the summation is going to become 1. Okay, that is why the curve lies inside the convex cell except in these 2 points. Is it
Sir,
understandable?
so can we say except alpha naught and alpha n, all the other alphas are dependent on alpha naught and alpha n?
Correct. It will dependent on the other one in the sense that it won't go to zero. All the others simultaneously won't go to zero except one guy. Okay. And that is because of t being some other value, not other than 0, 1. So if you put any other value, let's say t equals 0.5 or t equals 0.3, you can see that all alphas will have some values. Okay. So this should be 1. And that is the reason it becomes a summation of all that. And that is the reason why it will lie actually inside the convex cell, except in the degenerate case where we saw all are on the collinear line. Okay, all 3 points on the collinear line, but that's a very special case on that. Except that you can see that the first point and last point of the polygon points will coincide with your curve points on the t equals 0 and t equals 1. For all other t, you can see that it is going to be inside the convex. Okay, and this can also be explained by the basis function. Okay, that's what I was trying to put. So you can see the basis function behavior like this. This is for n equals 2 guy and n equals 3. What are your observations? You just take a look at one of them maybe. So let's say you take a look at this guy. What are your observations? Again, the same similar idea. So what can you say about the basis functions?
Sir, so J2 0 and J2 2 are like reflections of each other.
So basically it's a symmetry structure, correct?
Yes, sir.
So you can see that you can flip the parameter t and 1 minus t. Okay, this is a little bit too much, but you can start from this side and draw the curve. You get the same curve. That is the idea. Okay, if
Sir,
you start
just
from
a
B2 and you go to B naught, you'll get the same curve.
Sir, another question is what is the advantage of using binomial weights over, like, say, some other weights which are also having similar properties? So, say, like,
As
the
long as that is why we have a B-spline also, which has similar properties. Okay, but it will be more advantage and more complex. So you can bring in any such function that has these kinds of properties, and you show that it will follow these properties, then it is okay. That is what actually we have this as constraint basis function. We can get what is called as a B-spline basis function. Okay.
okay, sir.
So as long as you
Sir,
find some other function, who asked this question?
Sir, I'm Vignesh, sir.
Vignesh. So you can have a Vignesh basis function or something like that. Okay.
Okay,
So as long as this is this is called the Bernstein basis called Caldebur equation and found out. So you can also have Vignesh can have its own basis as long as you understood the idea, right? As long as you can bring out these properties and explain this thing, any other thing is fine. But BCR has been defined in this way because it has symmetry. You can see these basis function behavior. It is what are the things you observe apart from symmetry? What can you say about?
sir, I have a doubt.
Yeah.
Sir, are the constants the binomial coefficients because we are choosing like if we are choosing 2 points, it will be 2C naught. And I mean, sorry, if we are choosing
That will be
2
less.
points, yeah. If it's
Then you will
like
get the entire straight line itself. Yeah, that is more like no curve there, right? I mean, we'll probably use only from 2. Yeah, we can still talk about 1, but still same equation applies there on that.
no, so I'm asking like is the reason that Bernstein took the binomial coefficients because
Maybe. I
he
mean,
is
I know this
choosing
is possibly, but this
out
is
of
too
n
much
points
for
he's choosing r
answer, right?
points and then
Yeah. I mean, it could be, but these are all conjecture. I mean, I don't know how Bezier would have thought about it, but you're right. I mean, maybe these properties are so good, and Bezier probably used this expansion to do this curve. I mean, this is very. I probably cannot go into the mind of Bezier, right? And then probably what you've done. But But you can see that D Castley has done the same thing in a different way. Okay, before that, can you also tell some other implication of this basis function? What are the other things we observed, which we discussed in a different manner, but the same details can also be explained from here. What is that detail? Okay, let me ask, what will happen what is happening when t equals 0? Let's say take n equals 0. What is happening at t equals 0?
So it is monotonically decreasing.
Yeah, but can you put values to j functions?
Sir, the end function will be a linear combination of the three curves at any point.
Yeah, but what is the exact value of j to 0 at t equals 0?
So it will be 1,
Sir,
sir.
1.
J 20, you see the graph, it's there in the graph. J20 is 1 and all other functions are 0. That explains what? If you see this
It will be
equation,
B0.
J0 and J20, B1, J2. So all the other J's are 0, only this J is 1. That means what? You get the point B0 itself on the curve.
B0.
Okay, so this
And
is
then
just a
what
way
happens at t
to
equals 1? Say
visualize.
at t equals 1,
It will be
J22 is 1,
B2.
sir.
at t equals 1, J22
J2
is 1. All others are 0, right?
Exactly.
All others are 0. That
Yes,
what
sir.
does that mean now? Only
B2.
B2 is there and B0, B1s don't play a role. That means the final point on the curve is B2. But for any other point, you can see that not all basis functions are going to 0. Correct? If you take any curve like some t equals ti, okay, not all are going to be 0. But the summation will be there anyway. Okay, that is the reason why the curve lies inside the convex hull also. This is also another explanation that you can give. This is a very similar explanation, put it in a different form on. Okay, is that fine?
Yes,
Yes,
sir. A
sir.
minor
Yes,
question,
sir.
sir. Is it a coincidence that they're using T, or does it really stand for time?
Oh, no. I mean, T is also used for time in most cases, but in our case, yeah, I mean, T is space and time. All other parameters can be brought in. True, but it's not. I don't think that's the correct way of looking at this curve, at least. Okay, but
Okay,
T
sir.
is in many cases in many other books they use U also. Okay,
Okay, sir.
I mean,
Thank you, sir.
Roses and Adams happen to use the word T. I mean, T of course stands for time in other context also. Yeah, you can increase this to space, time, etc., and that those becomes parameters. Yes, but I think
So,
that is a little bit too much to visualize this on that manner.
Sir,
Yeah,
I asked
sir,
this because time actually fits perfectly here.
yeah, it's okay. I mean, what I'm saying is that we don't. You can say that the curve progresses in time from 0 to 1, something. Okay. Yeah, but we don't
sir,
usually visualize that in that manner. Yeah.
Okay, sir.
sir, I have a doubt.
Yes.
Are is J just a notation, or does it have anything to do with the Jacobian matrix?
Not in this case. No. I mean, Jacobian is only for derivatives, right?
Yes, sir.
This is only as a basis function. I mean, maybe right in some books you can see n. I think we'll see B-spline basis. We'll see n. No, it is not Jacobi. I mean,
Okay.
Jacobi. This is not a derivative matrix. Okay. So that matrix of derivatives is we go for Jacobian, then Hessian, and so on. You might have seen something in optimization, but it is not even derivative. Of course, you can do derivatives. I mean, then Jacobian matrix will play a role. We'll see that it's more on surfaces that will play a role when you have more parameters UV. Then you have to take the Jacobian matrix, but not in this particular case. Okay, we are
Sir,
not even seeing derivatives. Okay.
so in case we take a derivative of the Bezier curve, would it
Yes.
happen to be that these constants could be the
Correct. So
Jacobian
what you can do
elements?
is that you can find the derivative of j function with respect to t, okay, and then substitute t equals 0. What is your likely answer?
So the derivative of you mean
So
the
you take a
elements?
j function and find the derivative of the j function and substitute t equals 0 because this is also going to be a function of t, right? Because j is a function of t.
Yes, sir.
Sir,
Okay,
it's gonna
then
be the first
j
point.
dash is going to be a function of t, correct?
Yes, sir.
So if you put t equals 0, what is your likely answer?
So it will be 0,
B1,
sir. Oh, sorry,
Hmm.
1, sir. 1.
B1, B1.
Huh?
No,
Sir, the first
actually,
point. Actually, it
Okay,
depends on
I'll
the
give you a
Actually,
Pascal's
depends on the
triangle.
power, sir. The power will
Yes,
come
it
yeah,
down.
depends on
but
the
rough
triangle
idea,
itself.
which direction it will be?
So
It will be in the direction of that line segment.
Which
B1,
line?
B0, B1. Means from B1 towards B0. It will be like something
Towards
means
B2 or
some
it is, we
positive.
are starting from B0 though.
so it's the tangent,
Okay.
sir, of the
It's a tangent, but what
Yeah.
points will constitute the tangent in terms of control points?
B0
so
and
B1 and
B1. So
B1,
the
sir.
It
coefficient
is
of
going to be in
B0
the
will be
direction of
positive.
B0 to B1. Okay, so if you
Yeah.
derive it and you see that, okay, leave alone the factors like constants coming in. Okay, but you can see that it will go to be in the direction of B0, B1 line segment. Okay, that will be because that is how we drew the curve, right?
Yes, sir.
So at t equal to 0, it has to follow the tangent of the first or the line segment of the first polygon points, which is B0, B1. Okay, in a similar way, what will happen to t equals 1? What is your guess?
It will be the tangent Bn and Bn minus 1.
Correct. It will be in the direction of Bn and Bn minus 1. Fantastic. So you can see that we are not deriving anything. I mean, we can simply say, but of course, if you want to do exact attempt on more, higher level questions, you have to compute also. But you can see that we can answer all these things by, by using the logical reasoning on how the directions will be. And that is the beauty, in my opinion, of such functions. Okay, the Bernstein basis function, and is little bit complex is the B-spline basis function. Okay,